So the last time that we talked about nucleophilic substitution, we looked at this analogy. So take a moment and think to yourself what each of these scenarios represent. So the first three, and then the second three. And if you'd like to read more about this because you're curious, this is a great description from Master Organic Chemistry. So we're going to talk about nucleophilic substitution and what effect does the structure of the nucleophile have on the rate of reaction, as well as what effect does the structure of the haloalkane have on the rate of reaction, and what effect does the structure of the leaving group have on the rate of reaction, and then what is the role of the solvent. So in class today, when we were looking at this, we came up with two different mechanisms for the formation of products A and B. Do you remember what those mechanisms were? Go ahead and draw structures for the two products and explain how they're formed. How might you enhance the yield of B? And again, if you need to, go ahead and press pause as you think about this problem. When we consider nucleophilicity, we're really thinking about a kinetic property that's measured by the rate at which a nucleophile attacks a compound under a standard set of experimental conditions. So for example, it's the rate at which a set of nucleophiles displace the bromide ion from bromoethane and ethanol at 25 degrees Celsius. And so in order to make sense of this, one of the things we want to make sure we're able to do is to differentiate nucleophiles from electrophiles. So take a moment and circle any of the species on the first list that would constitute nucleophiles. And then take a moment and circle any of the species that would constitute electrophiles in the second list. And again, press pause if you need more time. When we think about nucleophilic substitution, one of the things we're concerned about is the effectiveness of a compound as a nucleophile. And so if we look here and we think about how we might classify these compounds, hopefully you're starting to think that anything like bromide or iodide would be a really great nucleophile, whereas anything that is not negatively charged, right, is not going to be as good a nucleophile. So it's going to be a more moderate nucleophile. And then there are nucleophiles that are actually quite poor, like water or methanol or other types of alcohols. So when we think about nucleophilic substitution, one of the things we want to talk about is the difference between SN1 and SN2 reactions. So for example, SN1 reactions are governed by electronic factors, namely the relative stabilities of the carbocation intermediates themselves. So these relative rates are tertiary, secondary, primary, and then methyl. So SN1 reactions are always better for tertiary or secondary compounds and very poor for primary and methyl compounds. The opposite is true for SN2 reactions. So they're governed by steric factors. That is the relative ease of approach of the nucleophile to the site of the reaction. And their relative rates go in the opposite direction. So methyl, primary, secondary are far more reactive than tertiary compounds. If we think about steric factors, one of the ways we can see this is if we compare the access to the reaction center for bromoethane and then for 2-bromo, 2-methyl propane. So for example, 2-methyl propane is the tert-butyl chloride part. And so if you think, ooh, in this case it should be bromide, not chloride. Sorry about that. Let's fix that. So if we think about tert-butyl bromide, right? This is our bromide, our really great leaving group, and then this is the backside. So that's all of these molecules. And you can actually see here how this is far more clustered or crowded than it is here for bromoethane. Best way I can think about this in terms of steric factors is actually to look at two examples of surfers. Here, right, this is not sterically hindered. It's open access. Anyone could get into that wave. Here, right, that wave is much more crowded. It's much harder to access. So we're going to take a moment and we're going to work through these problems. And one of the things we're going to do is look at different types of nucleophilic substitution. So let's talk first about classifying these nucleophiles. This is an example of a primary carbon. This is an example of a secondary carbon. This is an example of a tertiary carbon. How might those molecules react differently? Go ahead and take a moment, think about this, press pause if you need to. When we're considering nucleophilic substitution, we really want to think about the effect of electronic and steric factors in competition between SN1 and SN2 reactions of the haloalkanes. What do I mean by that? Well, if we think about the fact that SN1, or carbocation stability, is governed by electronic factors, then something that is a tertiary carbon is never going to undergo SN2. whereas primary and methyl carbons are never going to undergo SN1. So if we think about this in another way, really what we're saying is SN1 is always going to be governed by how stable the carbocation is, whereas SN2 is going to be governed by steric factors. How easy is it to access the site of a reaction? So when we're thinking about this in terms of nucleophilic substitution, the best leaving groups in a series are going to be our halogens. The reason that alcohols or water are such poor leaving groups is that they're rarely, if ever, displaced in nucleophilic substitution reactions. So really what we're talking about is the greater ability to act as a leaving group, or the stability of an ion, or the greater strength of the conjugate acid. And so the reason why we don't see these participating in nucleophilic substitutions or beta elimination reactions is simply because they don't make for very good leaving groups. Now, what does make for a really great leaving group is water. Well, how could water become a leaving group? Let's look at this example, and then I want you to go ahead and try to use that example to inform drawing the mechanism for 2-methyl-2-hexanol and its reaction with HBr. And again, take a moment, press pause if you need some time to think through how to draw this. One of the other considerations that we need to explore is the effect that solvents have on nucleophilic substitution. So a Protic solvent is a solvent that contains an OH group and is going to be a hydrogen bond donor. So examples of that are things like water or formic acid or methanol, ethanol, or acetic acid. These are all great examples of Protic solvents because they all have the ability to hydrogen bond. And it's this ability to hydrogen bond that is valuable because it actually stabilizes carbocations and it allows solvation. And so that's really helpful in terms of these reactions because we know that carbocations are all about stability. In contrast, if we think about aprotic solvents, so for nucleophilic substitution, an aprotic solvent is a solvent that does not contain an OH group and is not a hydrogen bond donor. So aprotic solvents favor SN2 reactions, and although the solvents at the top of the table are going to be more polar, formation of carbocations in them is more difficult than in protic solvents. So although these are polar compounds, they're not particularly good at stabilizing carbocations. So these are going to be solvents that favor SN2 reactions. So let's summarize what we know. If we think about this, here's a type of haloalkane. So methyl, primary, secondary, tertiary, and then substitution at the stereocenter. And it tells us whether it's going to be favored for SN2 or SN1. And so it's useful for you to start to create a chart to think about what's going to happen. So if it's a methyl, it's always going to do SN2. If it's a primary, it's always going to do SN2. If it's secondary, it is favored for SN2 when they're aprotic solvents, whereas it's favored for SN1 when it's in protic solvents. Tertiary never happens in SN2, but is favored in SN1. And then when I think about substitution at the stereocenter, it's always going to be inversion of configuration for SN2, and then racemization for SN1. Here's another way of thinking about that table when we're comparing the SN1 and SN2 reactions. So here, for the rate law, SN1 is unimolecular, it's only the substrate, where SN2 is bimolecular, it's the substrate and the nucleophile. The big barrier in SN1 is carbocation stability, whereas in SN2 it's steric hindrance. The electrophile is favored in SN1 strongly as the tertiary carbon, whereas in SN2 primary and secondary are favored instead. And then when we think about the nucleophile, generally speaking, for SN1 we want a weak nucleophile, whereas for SN2 we want a strong nucleophile. And then when we think about solvents, we favor protic solvents for SN1 and aprotic solvents that are polar for SN2. And again, when we're thinking about stereochemistry, SN1 is this mix of retention and inversion, whereas for SN2 it's always just inversion. Last thing we're going to talk about is beta elimination. So this is the removal of atoms or groups of atoms from adjacent carbons to form a carbon-carbon double bond. So we're going to study a type of beta elimination called dehydrohalogenation. This is the elimination of HX. So this is where a base is going to take a proton. The electrons from the bond between the hydrogen and the carbon are going to drop down to form a double bond. But since carbon can only have 8 valence electrons, it's going to kick out this leaving group, forming a double bond. It's important when we think about how to draw these mechanisms that we consider Zaitsev's rule. So the major product of a beta elimination is the more stable and the more highly substituted alkene. So when cis-trans isomerism is possible, the trans isomer is always going to be favored because it's going to be more stable. So take a moment and draw what this product would look like. Were you able to draw two products? And were you able to identify that 2-methyl-2-butene is the major product because it satisfies Zaitsev's rule? Let's take a look at another example. Press pause if you need to, or check your answer. Again, were you able to identify both products and which is going to be the major? In an E1 elimination mechanism, this is one extreme where I break the carbon-halogen bond completely before I react with the base to break the carbon-hydrogen bond. So only Rx is involved in the rate-determining step. Whereas in E2 mechanisms, I break the carbon-halogen bond and the carbon-hydrogen bond at the same time. That's what we refer to as a concerted reaction mechanism. They happen at the same time. So both Rx and the base are involved in the rate-determining step. So let's look at a mechanism for E1. The first step is to break a bond to give a stable molecular ion. So the rate-determining ionization of CX gives a carbocation intermediate, which is what we see here. That carbocation intermediate and halide ion. Then we remove a proton by taking a proton away using a base. The electrons from this bond between the hydrogen and the carbon now come down to satisfy that carbocation, forming a double bond. In comparison, if we look at the E2 elimination mechanism, this is a one-step mechanism. All bond breaking and bond forming steps are concerted. So I simultaneously take a proton away and I break a bond to form a stable molecular ion. So I take my proton at the same time the electrons from that bond come down to form a double bond, and I kick out my leaving group. So if we think about elimination and E2, and we do a comparison for primary carbons, we don't see E1, only E2. For secondary, if we see weak bases such as water or alcohol, then we're likely favoring E1. Whereas if we have strong bases such as hydroxide or other types of alkoxides, then E2 is going to be favored. And finally, if we have tertiary carbons, the main reaction with weak bases such as water and alcohol is favored, whereas the reaction with strong bases such as hydroxide or ethoxide are favored. So let's talk about the comparison between substitution and elimination. Because many nucleophiles are also strong bases, oftentimes we will see both substitution and elimination reactions compete. So the ratio of substitution to elimination products depends on the relative rates of the two reactions. So which is faster, do you think? Nucleophilic substitution or beta elimination? When we're comparing SN1 versus E1, the reactions of secondary and tertiary haloalkanes and polar Protic solvents give mixtures of substitution and elimination products, and the actual product ratios themselves are difficult to predict. When we're comparing SN2 and E2, it's considerably easier to predict the ratio of SN2 to E2 products. The attack of a base on a beta hydrogen by E2 is only slightly affected by branching at the alpha carbon, so alkene formation is accelerated. Whereas SN2 attack of a nucleophile is impeded by the branching of the alpha and beta carbons. So elimination is likely to occur faster than SN2 or nucleophilic substitution, so we're more likely to see double bond products predominate. Your job is going to be able to predict reaction products for methyl and primary haloalkanes, which means you should be able to recognize SN2 and combinations of SN2 and E2, as well as E2 only, as well as for secondary and tertiary haloalkanes, where you're much more likely to see mixtures of SN1E1, SN2, and E2. So let's do some practice to make sense of this. Take a look at the following reactions and tell me whether or not they would be SN2, E2, E1, or SN1. And again, press pause if you need to. You can take as long as you need to think about and work on this problem. If you start to think about your reasoning for why you can identify a reaction as favoring SN2 or E2, and you feel confident using evidence to back up your claim, then you're well on your way to being ready to study alcohols, which is what we're looking at next class. Thanks again for your time. Have a great day.